So today's topic is Raman spectroscopy. So there are two important theory we have here. The first one is classical theory of Raman spectrum. The second one is quantum theory. So we are going to talk about these two theory for today. So according to the classical theory of Raman spectroscopy, this theory says that when we have a substance, okay, in that substance there will be electrons which is having a negative charge, and the nucleus is present here which is having a positive charge. Okay, so now when we connect this one to a static electric field. Okay, now imagine that this is the positive pole and this is the negative pole. So when we applied some static electric field, so now these negative charges will move towards the positive pole, and this positive charge nuclei moves towards the negative pole. So during this step there will be a charge separation between both the charges. So this charge separation produces the induced dipole moment. So because of this induced dipole moment, because of this charge separation, so induced dipole moment is producing. So imagine that the shape of the molecule is like this, and after producing induced dipole moment, the shape may change like this. Okay, that means there is some dipole moment is producing. So because of that reason, these molecules are active in the Raman spectroscopy. We can also say that polarizability. After molecule produces this induced dipole moment, the shape of the molecule is changing. So this now at this stage we call this molecule as a polarizable molecules. Okay, now the polarizability concept is anisotropic in nature. So there are two terms we have here: anisotropic property and isotropic property. So isotropic property means in all the directions. Let's take density is example for isotropic. Let's take a brick. Okay, so here you just see all the portions, they will be having a same density. So this is a isotropic property. Anisotropic property means, so just a pass an X-ray light on one substance. So this X-ray, the intensity will be different, and this will be different, and this will be different. So this comes under anisotropic property. So polarizability is a anisotropic property. By seeing itself we can say this one. See, here the size is less and here the size is more. So this comes under the anisotropic property. Just remember, polarizability concept is a anisotropic property. So now this induced dipole moment depends upon the polarizability plus applied electric field, nu equals to alpha E. Next, so because of this anisotropic nature of the molecule polarizability, it facilitates the molecules are active in the Raman spectra. And now we have CO2 molecule. So in the CO2 molecule we have 4 normal modes of vibrations. So in that, one is symmetric, then asymmetric, and two bendings. So we know the mutual exclusion principle. A mutual exclusion principle. So according to this mutual exclusion principle, if a band is active in the Raman, that will be inactive in the IR, vice versa, right? So we know that this symmetric one is IR inactive but Raman active. So this mutual exclusion principle is applicable only for the linear molecules. So CO2 is a linear, so this is not applicable for other things. Now these two are IR active but Raman inactive. Okay, so now I will explain why this is a Raman active, why these are Raman inactive. Take a CO2 molecule. First we will go for the symmetric. Symmetric means the both should be in the this way, so this is symmetric. So here we are just imagine this middle portion is carbon and this is oxygen and this is also oxygen, and we are just stretching them this way. Means when we are stretching them in this way, there is a some polarizability change, so some induced dipole moment is producing. So because of that reason, this symmetric one is active. Okay, so now we'll go for the asymmetric. Asymmetric means we'll keep one constant and we will stretch only one, another one will keep them as constant, like this. So this is a asymmetric, and now the whatever change is producing here after stretching, that will get cancelled by this one. Okay, so that way the induced dipole moment here, otherwise we can say that the polarizability will be 0 here. So whatever change is producing by this band, so that get cancelled by this. I mean whatever change is producing here, that will get cancelled by this. So because of that reason, the polarizability is 0 here. And when we see the bending vibrations, there are two bending vibrations, so that we can see one will be this way and another bending vibration will be this way. See, these are in opposite directions, so these are in opposite directions, so each one get cancelled by each other. So here also the polarizability is 0. So this way we can explain why the symmetric one is active in the Raman spectroscopy, why asymmetric and bending are inactive in the Raman spectroscopy. So this can be explained by using the classical theory of Raman spectroscopy. So now we'll go for the quantum theory of Raman spectroscopy. I hope it's clear, because in case of symmetric there is some change in the polarizability. So induced dipole moment or change in polarizability can be achieved by the stretching like this. So whereas in case of CO2, in case of asymmetric stretching, so we are stretching only one and we are keeping another one as constantly. So whatever change is producing here, that is getting cancelled by this one. So because of that, the change in polarizability is 0 in the asymmetric. And similarly in the bending, means two bending vibrations we have, so one will be towards this way, another one will be towards this way, so both are getting cancelled each other. So because of that reason, bending is also inactive in the Raman spectroscopy. And if you take water molecule, so this is the this comes under asymmetric top. So for this, like mutual exclusion principle applicable only for the linear molecule. So for asymmetric molecules, the bands are active in both IR as well as Raman. This is about the classical theory, and now we'll go for the quantum theory of Raman spectrum. So this is very important. Quantum theory of Raman spectra. So before going to this one, so we have to know about the elastic collision and inelastic collision. Elastic collision means so when we have a one molecule, okay, so that molecule we have hit with a proton which is having an energy of h nu, okay. So after hitting, there is a one state which forms here. We can represent that one like this, okay. Now so this state is called as virtual state. So this will be having very small lifetime, and after that again they will get separate, okay. And we can also say that like okay, that I will explain later. So initially we have a molecule which is having an energy of E. This is E is initial energy, otherwise we can take EA, initial energy, and EB is the final energy, and this is having a frequency of nu. Nu means initial frequency, and nu dash is the scattered frequency, okay. Now I explain in details here what I'm trying to say. So in the oscillating electric field associated with a proton of energy h nu, so that will interact with the molecule, okay. And now for a small time this will be in the new state. That state is called as a virtual state. After that now there is a chance that energy can transform from here to here or from here to here, and similarly the frequency also. If the initial energy and final energy is same, and initial frequency and final frequency is same, so this kind of collision is called as the elastic collision. If initial energy is not equals to final energy, similarly incident frequency is not equals to the scattered frequency, and this is called as the inelastic collision. After this state, the energy h nu of proton will be emitted as a scattered radiation, okay. So this is the actually mechanism involved. What is the elastic and inelastic collision? So now for elastic collision example is Rayleigh scattering. And now we'll see in the diagram format. Here we have a molecule which is in the ground state, and this is the excited state, and this is the virtual state, okay. So now the molecule is here, so we have hit with the h nu of proton energy. Now the molecule goes to the virtual state. So this state is here now. Now this will be returned to its original state by emitting some radiation, means whatever proton we used to hit, so that will be emitted here or scattered. So now the incident frequency and final frequency should be same for scattered. Here energy of initial energy and final energy. Similarly, incident frequency and scattered frequency both are same for this one. So this is called as a Rayleigh scattering. Rayleigh. Okay, so this is very easy to remember. And now we go for the inelastic collision. For inelastic collision, this is the condition. Okay, so here we have Stokes lines, then anti-Stokes lines. So these are very, very important. See, here also same. Stokes lines means this Stokes lines and anti-Stokes lines, they produces by the, like, first we will talk about Stokes lines, and here anti-Stokes lines. Okay, if initial energy is less than final energy and scattered radiation is less than incident radiation, so this is the feature for Stokes lines. And here it's opposite. Incident radiation is greater, so incident energy initial energy is greater than the final energy, and incident radiation is greater than the scattered radiation. Sorry, I think this is opposite. So if EA is less than EB, then frequency of scattered radiation nu b is less than, it's correct, I think it's correct. So this is the actual relationship what we have. So here